study the Indecomposables. Steinberg viewed as a VB ring. Oh yeah, someone asked what VB stands for. So there's this FI modules, which is finite sets and injections, and FB is finite sets and bijections, and then they changed F to V to be like vector spaces, even though it's not really vector spaces and bijections, the name. Okay, so yeah. I'm going to tell you about, remind you about Rognus's common basis complex that Benjamin talked about, and we'll try to sketch the proof that it's highly connected when the ring is a field, and then and compute the Cazul dual of Steinberg modules, again, only in the field case. And in the process, we'll get simplicial complex models of the EK homology of Steinberg modules. And probably run out of time, but if we have time, I'll say something about versions of this story for symplectic groups and for automorphism groups of free groups. And R is a PID, F is a field, K is the coefficient ring. Conjecture. Okay, so we need the common basis complex. So for V, a finitely generated free R module. C has vertices. Summands W not equal to 0, or V, and V0 through VP. Form a simplex. If there's a basis, Bn of V with each Vi equal to span of a subset of the basis. Yeah, so let's get a little more familiar with this condition of having a common basis. So if the ring is Z and V, let's say, is Z squared, I'm going to conflate, by these vectors, I mean their span. So vertices are spans of unimodular vectors, like rank 1 summands in Z squared. So these three things are vertices, and we have edges from here to here and from here to here, and there's no edge from here to here, and the reason is because the determinant is 3, and if you have a basis, the determinant will be plus or minus 1. On the other hand, if we're working over Q, and we're there would be a edge from here to here. So, the vertices of this complex are the same as the vertices of the Tietz building. And in the Tietz building, it didn't matter whether you worked over a ring or over the field of fractions, but here it really does. Maybe here's another example. Let's say V is a three-dimensional vector space. P1, P2, P3, distinct two planes. Then the set P1, P2, P3 forms a two simplex if and only if their intersection is the zero subspace. Yeah, so if you, for example, had, having to be a geometric topologist to draw a picture, you had three planes that intersected in a line. You can't find a basis such that these three things are spans of the basis. You can convince yourself that you're going to need one vector on this line, and then you're going to need, you definitely need one vector in each of the three planes that's not on the line, and then that's four vectors, and four vectors is not a basis. Yeah, and this is related to inclusion, exclusion, which Oscar mentioned. If the intersection is zero, then you sort of have an inclusion, exclusion formula for the dimension of the sum. But otherwise, but like, for example, if they intersected in a line, you would do inclusion, exclusion. One other, maybe it's more of a remark than an example. R equals F. If you have two flags, then their union is a simplex in the common basis complex. So if you're working over a field and you have two flags, you can always find a common basis. This is something related to the Tietz building actually being a building. On the other hand, if your ring is not a field, this fails. Like, this is a flag with only one element. This is a flag with only one element. There's no edge between these two because they don't, there's no common basis. Okay, so the original motivation for considering this, slightly exotic simplicial complex is this theorem of John Ragnus that says let Fnk R be the nth stage of the stable ring filtration. So here Kr means the algebraic K-theory spectrum for the ring R, and you, what do I mean by the nth stage of the ring filtration? You use the iterated Waldhausen model for this space, so that describes this space as involving diagrams of submodule, or involving diagrams of modules, and you just take only those diagrams that involve modules of rank less than or equal to n. And the end of the theorem says homology of this complex is isomorphic to the reduced homology of GLNR with coefficients in the reduced chains on the common basis complex. This is my notation for the common basis complex of Rn. Yeah, so he used this to compute that K4 of Z is 0. If you know the homology of the K-theory spectrum, then you could use one of the standard machines like an atom spectral sequence to attempt to, or a Postnikov tower to attempt to compute the homotopy groups. And if you have one way to compute homology is have a filtration with a somewhat understandable associated gradient. So in particular, if the if this space is highly connected, then these equivariant homology groups have a vanish in a range, and so you get a vanishing line in your spectral sequence, and it makes it easier to compute. You still need to engage with the non-zero part. Okay, yeah, and so then his conjecture, as Benjamin mentioned, CVNR is 2n minus 4 connected if R is Euclidean or local. Okay, and so a thing, I'll move first. Oh yeah, maybe I'll save in words. So Benjamin's talk, he pointed out that there's a model of this that's 2n minus 3-dimensional. So this, even though this simplicial complex, its dimension is grows exponentially with n, its homotopy dimension is just 1 above the conjectured connectivity range. So this is equivalent to conjecturing that this is a wedge of spheres of dimension 2n minus 3. Okay, and Oscar sort of ran out of time before stating this, so Oscar and co-authors proved that there's a bunch of ranges and shifts that I'm probably going to screw up in this talk, so hopefully this one is fine. 4 if f is infinite. So they proved when R is an infinite field, they established. So the reason why you'd be interested in the conjecture is to get a vanishing line in the spectral sequence, and they established that vanishing line for infinite fields. And then we sort of copied their proof, added one lemma, and upgraded it to a connectivity result. Myself, Peter, I almost wrote Peter, and Jenny, that this is 2n minus 4. So we proved the conjecture in the field case. The conjecture is still open. In particular, if you could show it for z, it would imply K12 of z is 0. Okay. So
Still for infinite fields?
What?
Still for infinite
No.
fields?
Yeah. So they use the Nestorenko-Suslin property, which requires infinite fields. Yeah.
I think for semi-local wings with infinite residue fields.
Oh yeah. Our argument would work using your stuff too. Yeah. Yes. If you, yeah. I think. we're scared of those rings, so we just did it for fields. Okay. Oh yeah. So yeah, we just proved some lemma that avoids the Nestor-Eko-Suslin property, which has the advantage of we don't need to use infinite fields, and we don't need to take group homology. On the other hand, using the Nestor-Eko-Suslin property allows you to get at the E infinity indecomposables of the general linear group, which our work doesn't say anything about. Okay, so the main point sort of isn't that a bunch of homology groups are zero. The main point is, what do these homology groups mean? Whether or not they're zero, I want to tell you what they mean. Okay, so let's see. Homology. Steinberg. Yeah, so theorem. Lots of theorems I state have a analog after taking group homology, which is due to those guys, which I won't state. So yeah, so we prove that the homology of the common basis complex measures the commutative homology of the Steinberg object, which is a ring in this VB sense.
Is that E infinity?
What?
Is that E infinity commutative?
Well, E infinity and commutative are the same because of this comment about like symmetric groups. Yeah. Yeah, like in contexts where they're different, you want E infinity, but in this context, they're the same.
Yeah, I just wanted. Maybe was not clear that this is the same as what Oscar was talking about.
Oh yeah.
If they're the same, why do you need a different name?
I don't know. It's E infinity. Okay. Oh yeah, and then the second part is the associative, or say E1. Is so we compute that the associative homology is given by the sequence of Steinberg modules, pointwise tensor themselves, and these results are going to combine to prove the connectivity conjecture, at least homologically, because this is for formal reasons a vanishing line for associative homology, which I'll remind you what it is, gives you a vanishing line for commutative homology, in this case the same vanishing line, and then the commutative homology is equal to the homology of the simplicial complex, and that checks that the homology of the simplicial complex vanishes in a range, and you can very easily by hand check that it's simply connected when Rognus asks that it's simply connected. Okay. This is true for all PIDs. This we only know is true for fields. We'd expect the 0 to still hold for Euclidean rings. Oh yeah, the Rognus connectivity conjecture is false for PIDs, or like you can't generalize it all PIDs. I guess for n equals 2, it's equivalent to GLN being generated by elementary matrices, which often does not happen. Okay. So now I'm gonna rehash Oscar's story in maybe a way that be less elegant, but here we go. Okay, so I'm just gonna think A is a graded ring, and then we'll eventually I'll be like everything, do the same story for VB rings. I want a graded ring. I want it to be connected. So it's an n-graded, natural numbers graded ring, and I want A0 to be the coefficient ring. And then we have this decomposables functor. For me, it'll go from connected graded rings to the graded K modules, and it's given by the formula. Basically, you just mod out by products of things in lower degree, so the co-kernel A plus B equals N, A and B bigger than 0, AA tensor AB goes to AN, and we'll just set it equal to 0 if n greater than 0, we set it equal to 0 and yeah, so if you plug in, say, a polynomial ring, you get out the generators. Same thing if you plug in tensor algebra. And then we're going to be interested in the derived functors of this functor. HI com be the ith left derived functor of Q viewed as a functor from commutative rings space to K modules, and similarly HI associative is the same thing. So now we're viewing Q as a functor from the category of graded associative rings, K modules. Yeah. So what is this thing measuring? It's measuring relations as an associative or commutative ring. Yeah, we take the same functor, but same formula for a functor, but we view it as a functor out of two different categories, and we get different derived functors. So H1 H1 com K of xy will be K, and this is generated by, in some sense, you know, the commutator, sorry, H1 associative. On the other hand, H1 yeah, so so H1 is measuring relations. As a commutative ring, this has no relations, so there's no commutative homology. As an associative ring, this has relations. The two generators commute. That's not guaranteed for an associative ring. So you pick up a term. And yeah. I wrote the same thing. Thank you.
Do you think they're now bi-graded?
Oh, yeah, they are graded. Whatever, where this appears will depend on the grading of x and y, which I didn't tell you.
Yeah, so the ring itself is graded, and then you also have a homological grading because it's a derived functor.
Yeah, yes. Yeah, and whatever grading these things are in, this formula will tell you what grading you should put that in. Okay, so, oh yeah, and maybe to make things.
So it's bi-graded?
X and Y should have a grading.
Yeah, but the answer.
Yeah. Oh yeah, it goes to graded. I was running out of space. Yeah, so the functor lands in graded K modules. Yeah, so you prefer Tor groups. The associative homology is just given by Tor. So the coefficient ring is naturally a module over the ring because we assume the ring is connected. And this associative homology is just these Tor groups. Okay. So let's quickly review VD modules. So VD is the category of the good chalk is too short. Oh no, this is category finitely generated free R modules and isomorphisms as morphisms, and it has the symmetric monoidal structure coming from deconvolution. So if you have two VV modules, meaning functors from VV to K, the deconvolution tensor product evaluated on V, direct sum of U plus W equals V, and U tensor and W. And you can define, I guess I probably could have done it up there. I'll just right here, you can define this Indecomposables functor. So if A is a VV ring, meaning a monoid object with respect to this monoidal structure, then we define QA with a similar formula. So we just set it to be 0 if V is telling you its value on V. So this is going to be, this thing's going to be a VB module. Its value on V is going to be 0. If you plug in a zero-dimensional vector space, and it'll be the co-kernel of things in lower degree. Otherwise, AU tensor AW mapping to AV, and you sum over internal direct sum decompositions of V, and again, we require that this is non-zero. So we're taking all, in the VB sense, we're looking at all the things coming from smaller vector spaces, and we're just modding out by it. And this a lot. Now you do the same thing. You define commutative and associative homology for VB modules as the derived functors.
What's A of V?
Oh, so A is like a ring in this category. And instead of, before I told you, what is this in grading N?
Yeah.
And now, instead of the grading being natural numbers, sort of the grading is modules. So this thing is a functor from VB to K modules. So I need to tell you the value of the functor on a finitely generated R module. And then this is the formula. Okay. So we have Oscar mentioned we have bar constructions in this context. So if you have a VB ring, you can let the A of it be, maybe I'll conflate simplicial objects and their associated chain complex. All these tensor products are deconvolution. Maybe I'll just write it only the first time. And the base maps are given by the fact that K is an A module, gives you a map from this to this. A is a ring, so there's a map from this to this. Similarly there. Yeah, and the associative homology. Homology of a bar construction, and as Oscar mentioned, I guess the E infinity homology is can be computed by iterated bar constructions. This is, let's say A is commutative, and you like operads, the EJ homology can be computed by iterating the bar construction j times. Okay. And Oscar mentioned a
Did Oscar have some kind of shift in that bar construction?
J. Which one is J?
Under the color.
Colon J. What was the other objection?
Oh, it's not an objection, as a clarification question. Did Oscar had some kind of shift, like a bar and shift or something, and I forget why.
I think.
Oh, that's
I didn't.
I see.
Yeah. I believe I could have gotten it wrong, but I attempted to.
I think there's more chalk on
This. So Oscar mentioned a simplicial complex due to Ruth Charney that measures the associative homology of Z underline. So Oscar roughly said that there's a simplicial complex called the E1 Tietz building. This is just the associative homology of the Z underline. Remember, Z underline is the VB ring whose value is just Z everywhere. And I'll remind you what this thing is. This is the realization, the geometric realization of the simplicial set with P simplices, tuples of summands that add up to the whole vector space V. Yeah, and if you want to think of it as a semi-simplicial set, then you require these to all be non-zero. If you're thinking of it as a simplicial set, then you allow them to be zero, but then when you mod out by the face maps, you end up with the same thing. Okay. Yeah, and Ruth Charney proved that this is spherical. Okay. So, using this simplicial complex and the usual Tietz building, we can define these higher Tietz buildings that are going to measure the EK homology of Steinberg modules. This board. Okay, so higher Tietz buildings. Okay, so the simplicial complex TAB of B. This is the subcomplex. I'm going to view this as a simplicial complex. So you take the join, the simplicial join of A many copies of the usual Tietz building, and you take B many copies of Charney's split Tietz building. So, you know, vertices here are flags, or sorry, simplices here are flags, simplices here are splittings. Before we take the subcomplex, this whole thing is just A different flags and B many ways of writing V as a direct sum decomposition. And we take the subcomplex of collections of submodules with a common basis. Yeah. So, yeah, we have the simplex, so that's a possibly empty flag in here, a possibly empty flag in here, etc. Possibly empty flag in here, possibly empty direct sum decomposition of V, another direct sum decomposition of V, etc. And we require that the union of all all of those subspaces that appear anywhere, that has a common basis. T10, V is just the usual Tietz building. We just have A is 1, so we have one of these. We have zero of these. Every flag has a common basis. Similarly, T01 is just the E1 splitting complex of V, and the the observation that Oscar mentioned. This is the only situation where being a field matters. T20 is in the field case is just the join. So this equality follows just from the fact that over a field, any two flags always has a common basis. And in particular, because the Solomon-Tietz theorem says this is a wedge of n minus 2 spheres, this whole thing is a wedge of 2n minus 3 spheres, which in particular is 2n minus 4 connected, which is the connectivity we're going for in Rognus's connectivity conjecture. Everything else in the story works for general PIDs. This is the only part where we use PIDs. Okay, and analogous, so Oscar explained why chains on this simplicial complex are the same thing as the bar construction, or maybe you did like homotopy orbits, so you had to also say Shapiro's lemma. But an analogous argument to this tells you the following. So it tells you that this one, I don't have the shifts written down. So it says if you take the J-fold bar construction of the Steinberg module and you plug V in, this is equivalent to chains on the Tietz building of V. This is the J. So each time you take a bar construction, you get so sort of the Steinberg module is basically the same thing as T10, and every time you take a bar construction, it increases the amount of split directions you have by 1. Okay, so so a corollary so I guess maybe the corollary is that the EJ homology of Steinberg is just the homology of this simplicial complex, and then you can send J to infinity. You get the commutative homology of Steinberg. This is a reduced homology of the colimit of these complexes as J goes to infinity. Okay, so so remember I stated that the commutative homology is supposed to be the common basis complex. So how do we, so we want to now see that this simplicial complex is the common basis complex, is homotopy equivalent to the common basis complex, And if we can do that, then we've proven Magnus's connectivity conjecture. Oh, maybe I should point out, no. Okay. So, Magnus already had these models, some of them. I guess the case when B is 0 appear in Magnus's paper. The cases where either A or B is 0 appears in Oscar's paper. So Magnus had proven that the common basis complex of V is homotopy equivalent to the colimit as A goes to infinity of TA0. Back when I was optimistic, I had written a proof of this. It's pretty short, but I'm not going to have time for it. So the main sort of technical lemma that we prove is the following. So it says if A is bigger than 0, so there's a natural forgetful map that takes a splitting and turns it into a flag. If you have a splitting, you just remember the first term is contained in the first term plus the second term, is contained in the first term plus the second term plus the third term. So there's a natural map from here to here that turns splittings into flags. And the proposition is if A is bigger than 0, so if you have at least one direction of flags, then forgetting all the splittings and turning them into flags is a homotopy equivalent. So this is our replacement for the Nestorenko-Suslin property. Yeah. So see corollaries of this, and then see. Oh, am I out of time? Okay. I have a picture of that in the two-dimensional case, but maybe instead of gesturing at why that might be true, I'll just say how you use this. So, proof of the connectivity conjecture. So, so the associative homology. I want to get my. The associative homology of Steinberg. In the field case, this is the homology of this T11 complex. Here we have the field isomorphic to the homology of this T20 complex by our lemma. And now this is, we said this is a joint. So this is just T of Fn, join T of Fn. And this thing is highly connected. So this is zero if I is less than n minus 1 and it's Steinberg and F, tensor Steinberg and F in the top degree. So this gives us a vanishing line for associative homology, and So this tells us that the commutative homology of Steinberg is 0 in the same range, 0 if I is less than n minus 1. On the other hand, problem is I'm like deviating from my talk notes. Let's say my and this is, let's get the shifts right. For almost by definition, this is the homology where you have one direction of flags and infinitely many split directions, but then we can forget them into flags. So now we have infinitely many flag directions and no splitting directions. And yeah, and then this complex is homotopy equivalent now to the common basis complex. So the only situation where we needed fields, this was exactly this equality, where we wrote the join and used that the join was highly connected, and then so the this simplicial complex measures the associative homology. So we get a vanishing line for associative homology. That implies a vanishing line for commutative homology, which is just the homology of the common basis complex. So we get a vanishing line here, and you can promote it to being highly connected by checking that it's simply connected, which isn't that bad. Okay, I'll stop. Yeah.
Sir, well, I only know some Hauschild homology of some associated rings, so I don't know whether it's generalize that story or.
Hochschild homology, you know, if you do like Hochschild homology with coefficients, then the associative homology is Hochschild homology of A with coefficients in K.
Okay, it's correspond to the associative. Okay.
Yeah.
Just closing the
Oh.
nose.
All right.
This one as well.
It was the other one was the correct one.
The other one was.
Now it's just closing the shades instead of closing the
I'm using how close, like how slowly the window's closed.
Relation zwischen den Erzeugern.
Stop the recording.
Okay.